How does one implement a microservice correctly? Are microservices even useful? Just what is a microservice anyways? The best arguments for implementing microservices are organic. That is to say that the need for microservices evolved symbiotically within environments such as Lyft and Pivotal Labs. These initiatives were trying to solve the age-old problems of multi-team collaboration, service composability, and reproducible deployments on a standard platform. But there are times when the trade-offs of microservices are not worth it. Distributed systems are hard. Monoliths are easier. When you have a single team and no one outside that team consumes the team's microservices will tend to be overkill. Microservices require unique performance tuning. They dictate a very customized memory management strategy when advanced memory management is needed, and so are not suitable for all workloads. We can define microservices as somewhere on a spectrum between thick and thin implementations. A thick microservice definition is any software that a product team produces. The rate of change of modifications to the service is the same as the product team's rate of change. A thin microservice definition would be any software that has one concern and is deployed in a coarse-grained manner. This is to say that the software's functional requirements are loosely coupled and deployed separately. Whatever is deployed, however, is deployed with all of its dependencies. The thick strategy for microservice implementation is to have it built by a product team, which is a team that is responsible for gathering requirements, developing the code, deploying it to production, and maintaining it. There is no handoff to another team for any of these steps. The thin strategy for microservices involves deliberately developing the code in a coarse-grained manner so as to have all of its dependencies deployed with the code. Currently, the normal way of doing this is through containers. There should be only one concern per container. This translates into one process type, such as a set of Nginx processes, and not multiple process types, such as including MySQL processes in the same container. These containers should have a quick startup time, hopefully somewhere around 30 seconds. Because these containers are hosted in registries and downloaded, they should also have a relatively small size, such as 1 gigabyte or less. What does a healthy microservice look like? Some of the more insidious problems of managing microservices come from inappropriate memory and lifecycle management. To solve these problems, you need to use a proper init system. This is to say, you need to use a parent process that passes on the sigterm signal to its child processes, such as dumminit. This parent process should also be sophisticated enough to reap zombie processes as well. Failure to do either of these can create serious memory leaks or corrupted data. For high-performance communication between containers, inter-process communication can be used to circumvent the network stack instead of adding multiple process types in one container. There are two methods for controlling the creating, updating, and deleting of coarse-grained artifacts such as those used for microservices. Method 1 is using an orchestrator such as Kubernetes. Method 2 is using a service mesh such as Envoy to route and load balance traffic to microservices. In Method 1, the containers are deployed in pods and watched within a reconciliation loop. The orchestrator will continuously try to bring the state of the microservice to the predefined state associated with it. The microservice exposes an API that lets the orchestrator know it is ready to handle traffic. In some cases, when the pod's application has unique states during deployment, such as a database, the pod will utilize stateful sets to track the deployment state. In Method 2, the containers are deployed using whatever deployment tools are preferred, but the discovery, life, and termination of the microservice is tracked by the service mesh. When traffic becomes abnormal, the service mesh tries to establish the connection and eventually stops routing traffic to that microservice. Any problems with deployment are diagnosed using observability tools and remediated manually or through other means. When using an orchestrator like Kubernetes, it's best to have a standard way to express the deployment of the microservice. This can be done by converting Kubernetes manifest files into Helm charts or by using kept. For more complex deployments, Kubernetes operators can be used. Following a GitOps strategy by having another operator that watches for changes to these installation files in Git while triggering deployments is also an option. With the advent of cloud-native technology, the burden of performance tuning is pushed back onto the development team. This is in line with the product team's responsibility of maintaining code all the way into production. In order to separate the concerns of the platform maintainers and the infrastructure architects from the microservice developers, it has become the best practice to expose the internals of the microservice to the platform. The names for these techniques are observability and telemetry. Metrics, tracing, and logging are all forms of observability and telemetry that give visibility into what is going on in production to the product team. When implementing observability with large deployments, it is important to prioritize pulling data from the microservice instrumentation APIs instead of pushing in order to reduce load. Kubernetes was first designed to support stateless workloads and is still most efficient when dealing with these types of workloads. The capability for stateful workloads, such as databases, was added later. When dealing with microservices that have their own databases, it's best to use elastic block storage and avoid sharing the database between microservices. Transactions between microservices, also known as distributed transactions, should be avoided but can be supported using tools like OpenXA and the Saga pattern. The most common anti-pattern for microservices is the lift and shift. This is when someone takes a full application, a monolith that has many concerns such as a web server and a database, and puts them all in one container. The rate of change for all of these concerns will cause continuous restarts and redeployments in lockstep. Another anti-pattern is ordered pods. This is when the startup sequence of one pod or container is dependent on another pod or container. Pods should be resilient enough to re-engage with their dependencies if they are not active yet. Another common anti-pattern is a microservice that requires privileged mode in order to operate. Microservices should be platform and host independent when possible.